Good morning, everyone. Thanks for coming. It's great to be here speaking about our more or less last year work. And before we can go through the most interesting stuff, a little bit of formalities. Okay, better, okay. So we are. My name is Saverio Veltri. I'm solution architect at Radicalbit, and here with me there's Paolo Mascetti, data and software engineer at Radicalbit. So Radicalbit is a company 100% Italian, like Ivano just said, and it was born in Milan in 2015. And our core business is the development of something called event stream processing product and solution, basically analytics platform based on streaming systems. And okay, so how the talk will be structured. There's going to be an introduction followed by a brief description of the NSDB main features. Then Paolo going to talk about how we architected the actors and all the components in the single node design. Then I'm going to give a little bit of background about Akka cluster, and then we're going through the distributed design, and to conclude some roadmap, open source considerations, and something if you want to contribute to the project. Okay, so in the introduction we are going to talk about why we decided to develop this product, its main connotation, the model we use to build it, the consistency model, and an example of how you can use NSDB in a very common data-intensive architecture, which is CQRS. So let's say that when we start our core business, we were looking for a product able to fit, of course, our requirement, but honestly, we weren't able to find anything that simultaneously satisfied us in terms of licensing and in terms of requirement fit. So we decided to develop something from scratch, also because we really care about having strong knowledge and also some really good Scala code base. Okay, so some connotation about NSDB. NSDB is distributed. It's based on Akka cluster, so it's possible to deploy peer-to-peer cluster nodes. It's time series, so it's not general purpose. It's optimized for time series management, and it's streaming oriented. We will see later this peculiarity. Okay, so first of all, what is a time series record? It's important to describe it in order to take in order to our future treatments. So. Time series model, we can use the metaphor of an observation of a phenomenon which evolving in time. So the value is the phenomenon value observed. The timestamp is the time instant in which the observation occurred, and the dimension and tags are characteristic of the phenomenon observed. For example, I don't know, the location in which the observation took place, the temperature, and many other features. The difference between dimensions and tags is that dimensions can be used for SQL projection operation for SQL work conditions, and tags can be used also for group by operations. Bit, which is the name of our time series record, is immutable, which means that it's possible, of course, to insert bits. It's possible to delete them, but it's not possible to update them. Also, the schema is monotonic, which means that there isn't a fixed schema, but it's possible to only to add fields to an existing schema, not to modify existing fields. Also, of course, there are a hierarchy of bit containers, the metric, which is a series of bits, the namespace, and the database, which is the top level bit container. The first important concept we'd like to explain is the consistency model. Let's say it clearly, an STB is eventual consistent, which means that the effect of write operations are visible only after a certain amount of time. But there is a peculiarity. If clients can be subscribed to the database providing a query, and if it happens, when a record is inserted into the database, it will be first forwarded to the publish flow subsystem in a near real-time fashion, and it will be forwarded to the subscribed clients. Then, eventually, it's written in internal storage and available to any other clients. So these couple of features, so the eventual consistency and these push capabilities, narrows down the point of applicability of NSDB. Of course, NSDB, you can't use NSDB if you want consistency, but you can use for the serving layer, for example, on the read side. So, for example, this is an example of a CQRS architecture in which NSDB has been applied. And the CQRS architecture is based on the clear separation, the segregation of write operation, which are called commands, and read operation, which are called queries. So the scalability is being achieved by the fact that it's possible to separately optimize write and read operations. And of course, NSDB cannot be used for writing purposes, but it can be used for executing queries on data projected from the write database. Okay, Paolo?
Okay. In this section, I'm gonna lead you describing the main features of NSDB. For example, the concept of natural time sharding, how it is applied into the data partitioning, and we're going to describe the APIs and built-in connectors, and at least we're going to describe from a high-level perspective the publish-subscribe mechanism. Being time our first class measure inside the NSDB, we created the concept of natural time sharding. Based on this concept, we collected the data points into so-called shards based on points event time, like in a streaming fashion. Any other partitioning over data are demanded to the persistence layer, in our case, Lucena. This mechanism is applied independently to each metric, so the user, when write the first bit of a metric, can decide the shard interval for the specific metric. This configuration really depends on the frequency of the data and the read access pattern that the user wants to perform. And being data just added and not updated allows us to concatenate data chunks and never merge them. Okay, thank you. How this concept is applied to write operation? When a data comes inside the system, it's handled by a write request of data is handled by a write dispatcher. And based on the shard interval, the data is written into the correct shard, maybe in one location, and when the shard is full, another shard is created, and so on, maybe in different locations being distributed. Similarly, during read operations, the user can specify a query in a SQL-like language. In this case, there is also a where condition over time. And in this case, we could extract a time interval. Based on this time interval, we retrieve just a subset of shards, not every shards we have. We collect the results, and we reply to the caller with the the aggregated result. Now we're going to describe the API we implemented and connectors. We have Scala and Java APIs based on gRPC, and leveraging Akka HTTP, we also build HTTP, HTTPS APIs, and also WebSocket APIs based on Akka Stream, which are used during the publish-subscribe mechanism. And we have also some connectors like a Flink Sync and a Kafka connector. Here there is an example of the write APIs. The user has to connect to NSDB, specifying the host and the port. Then, using a simple DSL, the user has to define the coordinates of the bit, so the database name, the namespace name, and the metric. And then you can define the value of the bit, and optionally the dimensions and the tags. Similarly, for with APIs, the connection part is the same. The coordinates are the database namespace and the query the user wants to execute. Now we are going to describe from a high-level perspective the publish-subscribe mechanism. The user can subscribe to a specific query using the WebSocket APIs. If the subscription is successful, the historical data matching the subscribed query is returned to the user. And then, every time a new data is written inside NSDB, if this data match a registered query by the user, the data is published on the WebSocket channel previously created. Okay, now we are going much more in the technical part, and we are going to describe the single node design of NSDB. And to do this, we are going to do just a brief recap of Akka. Then we are going to describe the overall node architecture. We are going to also explain our storage layer and why we decided to use Lucene. We are going to talk about our SQL-like support language. And then we are going to describe how we wrap Lucene inside our service layer based on Akka actors. Then the actor hierarchy on the single node, and at last, the data streaming flow. Just the Akka recap. What is an actor? An actor is an object that encapsulates a state and a behavior. The actors communicate between each other, sending messages. Every message is in queue in the receiver mailbox. Each actor has only one mailbox. There are two ways to send messages between actors. The tell method that is called fire and forget, that has at most once delivery, and also the ask pattern, where an actor sends a message to another actor and it expects a response from the latter. Actors create naturally hierarchies because an actor can spawn children. When a child is created, the parent automatically supervises it. So if there are exceptions not handled by the child, they goes to the supervisor, in this case the parent. Now there is just the technological stack of NSDB. We have a gRPC server for Scala and write APIs, Akka HTTP for HTTP APIs, and so Akka Stream for WebSocket APIs. So also there is obviously Akka cluster for the distributed deploy, and a persistence layer. For the data, we use Lucene, and there is also a custom commit log storage. Our storage layer, as I said, is based on Lucene, And we implemented an ad hoc index management according to our concept of time series. And why we decided to use Lucene? Because it's a very stable and continuously improved project. It's very scalable, and the indexing and the queries are very performances. And it's also a very common choice in the field of databases, and the possible query optimizations are very powerful, and it's written in Java, so it's about easy to use inside our Scala code base. On the other hand, the documentation it's not the best, and most of it is outdated, and also it's Java. We would prefer a Scala implementation, of course. There is an example how we handle queries inside an SDB. User can specify a query using a SQL-like language, as you can see. The query is parsed by a Scala parser combinator. That is the first one, the part that matches the syntactical part of the query. Then there is a semantic parser that traduces the query inside an internal representation. And for the last part, our IDTs are transformed into a Lucene query that could run inside an SDB, inside the Lucene core. We use the Lucene in combination with Akka actors, because using actors and writing a layer over Lucene allows us to avoid the mess of lock and blocking. And each actor over Lucene handles just a single kind of operation, in our case, read or write on a specific entity. And using Akka actors allows us to scale up on a single node, for example, using routes. Here there is a schema representing the hierarchy of actors inside a single node of an SDB. There is an entry point that is the parent of everyone, that is the node actors guardian. Then there is a set of top-level actors called coordinators. Then there are node data actor that handles a request for a specific database namespace. Then going through in granularity, there are actors handling a request for a matrix. So we have the metric reader, the metric accumulator, and the metric performer actors. And at last, the actors handling shards, and so in our case, the shard reader actors. Here are just described the main coordinator we previously mentioned. We have the read and write coordinator, the publish for the publish-subscribe mechanism. We also have a commit log coordinator, a metadata coordinator that handles a request for NSDB metadata. In our case, for metadata, we mean the state we have to share between nodes, which are the shard locations and information about the metric, for example, the sharding interval of each metric. And the last is the schema coordinator, handling, obviously, the schemas. Now we are going to describe the write flow inside a single node, of an SDB. A write request comes to the write coordinator. It delegates it to the node data actor, and based on the metric where the write request must be performed, a message is sent to the metric accumulator, which has a buffer where accumulate all the write requests. Then there is a schedule that when it is triggered, all the buffered requests are sent to a performer that apply the real write on Lucene indexes. Similarly, we have a read flow where obviously the request arrives to the read coordinator, is delegated to the node data actors. And here there is an example where we scale up on a single node because we have a root of metric reader actors because we want to manage in a parallel fashion read operation on the same metric without being not so fast. And so when the request arrives to the metric reader actor, based on the reader request and so the shards that must be collected, the metric reader asks for the data, for the execution of the query to the shard reader, which have the interval inside the interval requested by the query. It collects the results, and then the result come back. Here there is just a piece of code of the previously described process of gathering the results from the shard reader actors by the matrix reader. And just maybe we can discuss later about it. The data streaming, now we are going to describe the data streaming flow just from the technical point of view. We already said that once a bit is received, is published, is being sent to the publisher actor, and so to the created channel on WebSocket using Akka stream flow. But we faced a problem during this design because there was an imbalance in terms of number and frequency between the comments messages and the events messages to be published on the channel. So it may happen that some subscriptions were not successful because they were processed too late for the user. And so we decided to use an unbounded control-aware mailbox that is built in Akka. And this kind of mailbox implements a custom mailbox that has two queues, one for common messages that have high priority, and a second queue for every other kind of messages. And this kind of mailbox guarantee us to process the control messages.
Okay, so now it's time to go distributed. But before we can go safely distributed, we need to make an overview of Akka cluster. Okay, Akka in general and Akka cluster specifically relies on the concept of location transparency, which means that it's possible to communicate to remote actors without knowing where they have been deployed. It's also possible, however, to specify the address we want them to be deployed, and we see later that we do it. Okay, so some feature of Akka. What's happening to the? Can you see the slides?
Just one screen.
It's happened sometimes.
Okay. Some feature about Akka cluster, it's peer-to-peer, which means that there isn't any single point of failure, there isn't any bottleneck, and this has been made possible by using a gossip protocol and efficient failure detection algorithm, probabilistic algorithm. It also supports an event-based notification, which means that it's possible to subscribe to cluster events in order to react to them. For example, if a node joins or if a node leaves. Also, it's possible to subscribe to metrics event, for example, memory and CPU usage. And it provides also a couple of useful extensions we leveraged a lot in our development. The first The first extension we leveraged is Akka distributed data. Akka distributed data is very powerful and useful when you have to share data between cluster nodes. So for example, if you have an entry and you want to be sure that this will be replicated among the cluster nodes, the most natural way is to use the Akka distributed data that allows it out of the box. We can think about it as distributed key value cache. It supports many data types, set, map, counter, and so on. And it supports different consistency level, which basically means that we can, for example, use the right local consistency level, which means that the record is written on the local node, then the Akka is returned, and then the other nodes are disseminated with the entry in an asynchronous fashion. But on the other hand, the biggest, it's not a problem honestly, but issue we have is that Akka distributed data is not designed to handle big data. According to the documentation, the maximum number of top-level entries should not exceed 100,000. So So it can be used only according to particular conditions. The other extension we used is the Akka distributed publish subscribe, which is very useful if you want to send messages to a set of actors which you don't know the existence. So, for example, as you can see from this code snippet, it's very easy for actors to subscribe to a certain topic, and it's also very straightforward to publish messages to a topic. The semantic delivery, of course, is the same as the tell pattern we described before. Okay, so let's go through probably the most interesting part. Let's hope. Okay, so NSDB adopt the multi-master replication distributed architecture. So as we said previously, when a node joins the cluster, we started to deploy actors inside of that node. There is a special instruction you can give to the props of the actor, which is with deploy, and you can specify the address. So as you can see from the picture, in this picture there are a couple of nodes, and every node contains the coordinators and the low-level actors. The multi-master replication means also that every node can be contacted from the outside in order to execute write and read operations. So there are many contact points in NSDB. You can contact every node, and every node gives you the write and the read capabilities. But in order to do this, it's essential that the coordinators are able to communicate to the low-level actors of their own node, but also that they have the references of all the other low-level actors. How we do this? We implemented a custom heartbeat protocol which leverages the distributed publish subscribe. So basically, every coordinator is subscribed to a dedicated topic, and also guardians are subscribed to dedicated topics. And there is a cluster singleton actor. Cluster singleton actor is another construct of Akka cluster which allows the existence only of only a singleton actor among the cluster. This singleton actor periodically asks guardians to send all the data, the actor reference they need. Of course, there is a sort of optimization. If a node joins, an add event, another delta event is disseminated, as well as if a node leaves, a remove event is disseminated. Okay, let's say that the most important part of the multi-master architecture is the replication. It's very important, and we adopt two different strategies in order to replicate state, which for us is the shared locations information and the matrix schemas, and one other for the data in itself. Since we estimated that in a normal scenario, the number of entries, the number of state entries will be lower than the threshold indicated in the Akka documentation, it's safe to use the Akka distributed data. Since we privileged the read performance instead of the write performance, we decided to adopt the write all consistency level and the read local consistency level. So which means that the write requests are going to be a little bit slower, but the read requests are as much faster as possible. We also put together the Akka distributed publish subscribe extension in order to implement a custom persistence mechanism added to the Akka distributed data. There is an official way to do this called the Akka distributed data durability. We are evaluating it, but so far there is this custom implementation. Okay, so for data, which is big data, it's actually big data, we use a custom approach. So we can define two different replicas, consistent replicas and eventual replica. When a write request is received by the system, the record before the Akka can be returned to the caller, it's important that all the consistent replica have been correctly, the data has been correctly written to all the consistent replica. The eventual replicas are written asynchronously, and also they fail silently. So, for example, what I've just said, but let's see it with the help of some graphics. So as soon as the record comes to the system, the first operation that has been performed is the record validation, which basically involves the schema validation. Then the consistency and the eventual write location are gathered. So the write coordinator will ask to the metadata system the write locations, given a timestamp. The write locations, the metadata system will return the consistent location and the eventual locations. Then we are ready to write the data. And first, the data are written to the consistent locations. Then the ACK is returned to the caller, and then silently the data is written to the eventual locations. On the other hand, when we want to read, when we want to execute a query, the first operation that has been performed is the time interval extraction, which has been made by using Spire. I don't know, I can see, okay, no worries. So we get a time interval that has been passed to the metadata system, which returns all the replicas. So as you can see, there is location 1 that belongs to node 1 and location 1 that belongs to node 2. Then those replica must be, let's say, reduced to one per location, to a set of distinct replicas for all the locations. And then, as Paolo mentioned, for the single node architecture, there is a parallel gathering of the result from the single shards. Then a post-processing phase is performed, which involves the concatenation and, in case, the ordering. and then the result are returned to the caller. Okay, now the most this is very scaring, honestly. I don't know how much time would we still have. It's 10 minutes. Okay. Okay, because we went a little quicker than we were expecting, so I thought we wouldn't have time to go in details through this topic, but let's see what we can do. Let's say that all this write to the replica process can be seen as a distributed transactions. That distributed transaction doesn't have the isolation property because the effect of a single write can be seen from the outside, even if the transaction is not terminated. So it's not possible to apply the two-phase commit protocol. So we decided and we adopted the Saga pattern. So we have still some minutes, so probably I don't have any information, but I can try to tell something about the Saga pattern. The Saga pattern is a pattern to handle distributed transaction that is basically that is based on the fact that every action, every atomic action belonging to the transaction must come to a compensation which roll back all the effect performed by the action. So basically, if the action is the insert a record, the compensation action must be to delete it. So a graph of actions and compensation is created, and if an error occurs during this graph flow, all the compensations belonging to the action executed previously must be applied. I don't know if this is clear, but I don't have any help from the... And of course, what happens if the compensation fails? If one compensation fails, this leads us to the next slide, which is a quote of a Victor Klang tweet, which is yes. So if we replace the phase one with action and the phase two with compensation, that's the feeling we have during the distributed transaction management. Okay, so now the conclusion. So of course there are many features that still needs to be developed. For example, enhanced location, the location selection algorithm, which now is a simple round-robin algorithm. We also need to develop a cluster monitoring tool. So logs are fine, but most of the time not too much. Also, we need to enable Kubernetes support. We need to introduce the concept of time to live for our bit, and also some improvement to the SQL engine, because so far we support the most common statement of the standard SQL, but we would like to support more constructs. Okay, so NSDB is released under the Apache 2 license. It's publicly available on GitHub. You can reach us there. Of course, as a company, we provide the Enterprise Edition, which adds, of course, a support and also some security integration with OpenID, for example, and also Kerberos. And also the metric versioning feature, which basically is which basically allows the existence of the same metric with different versions. And that's it.
Thank you. We have plenty of time for questions, so please raise your hand if you have something. Yeah?
So in terms of monitoring this system of actor Do you have any lessons learned to share, or any tool that you use for performance monitoring of, especially at the level of each actor? Because for my experience, this was the most challenging aspect of running a system of actors.
Yeah, of course, it's challenging, and it's part of our roadmap. The cluster monitor, also in terms of a single actor monitor. Okay, of course we implemented the supervision strategy, but we still need to find something more effective. I don't know if I've answered.
Any more questions? Okay.
Since we started the conference on this note, I think it's worth it to make a question about this. About contributions to these projects, do you, apart from this roadmap and reaching you on GitHub, do you also have maybe a mailing list or something shared for the community to maybe join the project and provide some contributions?
Okay. You're asking me if we provide any channel to communicate. Yes. So far, not. But you are free to go to GitHub and open issues. We'll discuss about them.
Thanks.
Anyone else? Don't be afraid. Okay.
Hello, thank you for presentation. I have several common questions about NSDB. Is there a way to remove data for previous period and inserting again with same time but different values, or inserting based only on current time? It's the first question. The second question is about performance. Do you give a comparison between InfluxDB or maybe Prometheus or ClickHouse, if you know? And do you have Grafana integration?
Okay, can you repeat the first question, please?
First question is about can I remove data of previous period and insert it again with the same time but different values? Or it's inserting based only of current time, like in Prometheus?
Yeah, of course you can delete previously inserted data, and you can write the same new data or bit with a new value with a timestamp in the past.
Okay.
Yeah, you can do this, of course.
Okay, thank you.
Regarding the performance question, we haven't published any benchmark yet, but we will do in the future. Let's say that we are pretty satisfied with the single node performance. We are able to handle millions of records without any gross problem. So, but we still need to perform more accurate benchmarks.
Okay. What about Grafana integration?
No, we don't have it yet. But you're free to try to contribute.
Okay. Okay, thank you.
Last question? Anyone? Think it through. Okay. Thank you again